In this lesson, you will explain how levers work, calculate moment, distinguish between different types of levers, state and explain the principle of moments, and define and calculate mechanical advantage. The key concepts in this section. Firstly, we'll look at turning force. We will look at the torque or moment of a force, the pivot or fulcrum of levers, the principle of moments, levers, first class, second class and third class levers, and the concept of mechanical advantage and calculations involving this concept. We're now going to look at turning forces. Sometimes a force causes a body to turn around a point. This point is called the pivot or the fulcrum. The effect of a turning force, which we call the moment, depends on two things: the size of the force and how far the force is from the pivot point. Let's look at an example. Now, this is a challenge to think about. If the same force is applied in these two cases, which has a larger moment? If the force is applied at that point, or if the force is applied at that point? We suggest that you pause the DVD and discuss this amongst the other learners and see what solution you come to. The solution to the two spanners, the answer will be the second spanner, the one on the right, because that force is applied a distance further away from the pivot point than in this case. Let's look at how we measure this effect of this force, which we call the torque or the moment of the force. The definition for the torque or the moment of a force is the effect of a turning force. The calculation or the size of the moment is given by the following equation. This symbol is torque equal to the perpendicular force applied times the distance from the pivot or the fulcrum. So this symbol represents the moment of the force. This symbol, the perpendicular force, which is applied at a distance r from the pivot, and r equals the distance from the pivot to the force. Let's look at that spanner example again. If this is the pivot, and this is the distance r from the pivot where the force is applied, that's measured by r in meters, the force is applied at a perpendicular angle to the spanner, that is represented by that symbol. Therefore, this moment or the effect of this turning force is calculated by this equation. The unit of moment is therefore, the force is represented in newtons and the distance r in meters, and therefore the unit of moment is a Newton meter. So remember, a moment of a force, which is also called the torque. Looking at challenge number 1. A mechanic using a spanner applies a force of 120 newtons to undo a bolt. We are asked to calculate the moment of the force if he applies the force 0.2 meters away from the bolt. We suggest you pause the DVD and complete this calculation. The solution to challenge number 1. The equation we use is torque or moment equals perpendicular force times distance from the pivot. And here we see the information gives us 120 newtons is the force applied, and the distance from the pivot to where the force is applied is 0.2 meters. Therefore, multiplying those two together, we get the torque equal to 24 Newton meters. We're now going to look at an everyday example where we use the calculation of the principle of moments. This is an equilibrium situation where things are in balance or balanced. So we look first of all at the principle of moments. What is the definition of the principle of moments? For any object that is in equilibrium, the sum of the clockwise moments about the fulcrum provided by the forces acting on the object equals the sum of the anti-clockwise moments about that point. Let's look at that. Here is a lever system with a fulcrum or a pivot point. And therefore, if a force applied on this side at a distance of 1,5 meters from the fulcrum, if we calculate the sum of the moment on this side, which would be 100 newtons times 1,5 meters, giving us the torque or the moment. Remember, this is the anti-clockwise moment, since this would move in an anti-clockwise direction. So the sum of these anti-clockwise moments, if this whole system is in equilibrium, will equal on the other side of the lever the force going down 150 newtons and the distance from the fulcrum. Remember, this is the clockwise moment, and we can say that this side of the lever will equal that side of the lever, and therefore we could calculate this unknown. Now pause the DVD at this point and see if you can work out the distance that would need to be placed for this to be in equilibrium. Remember, the sum of the anti-clockwise moments will equal the sum of the clockwise moments. Pause the DVD and calculate this distance. Looking at the solution to this keeping in balance, we needed to calculate this distance, and if we remember that the sum of the anti-clockwise moments equals the sum of the clockwise moments, you should have calculated this value to be 10 meters. Hope that you got this calculation correct. If not, try it again and make sure you're able to calculate this distance. We're now going to look at challenge number 2. We're going to consider a lever system with a mass of 6 kilograms on this side and a mass of 4 kilograms on this side. Remember, this would be moving in an anti-clockwise direction. If the distance of this mass is 90 centimeters from the fulcrum and the distance of this mass is 60 centimeters from this fulcrum, if we put a mass on this side of the lever system at a distance of 100 centimeters from the fulcrum, we now need to be able to calculate mass 3. So if the system below is in equilibrium, calculate the mass of object M using moments of forces. Remember, first step to convert centimeters to meters. Remember your anti-clockwise moment, the sum of the anti-clockwise moments equals the clockwise moments on this side. We suggest you pause the DVD at this point and do the calculation. Let's look at the solution to challenge number 2, and we hope that you've got this correct. First, summarizing all our data of the levers. Now we're going to look at the anti-clockwise moment on this side of the lever system. We first need to calculate the perpendicular force, and we are given mass, and therefore we need to use acceleration times mass to calculate the perpendicular force. 6 kilogram times acceleration 9,8 meters per second squared equals, and rounded off to 59 newtons as the perpendicular applied force. In this case, mass 2, the applied force of this will be 4 kilogram times 9,8, giving us, rounded off, to 39 newtons. On this side, we do not know the perpendicular force, and we are going to calculate this so we can get back to work out what the mass is. Let's look at the principle of moments. Remember, the sum of the anti-clockwise moments equals the sum of the clockwise moments. So therefore, torque 1, which would be this force, plus torque 2 using this force will equal torque 3 on this side of the lever system. Remember, the sum of the anti-clockwise equals the sum of the clockwise moments. Therefore, putting this into the equation, we get 59 newtons times, and remember, you must convert from centimeters into meters. So 90 centimeters becomes 0.9 meters times 59 newtons. And remember, it's a sum of the anti-clockwise moments. So we add this one, which is 39 newtons times 0.6 meters, must equal this force, which is an unknown, times 100 centimeters, which is 1 meter, and we solve for the unknown. In this case, you should get 76 newtons. So therefore, we need to remember the calculation asked for the mass, and since force equals mass times acceleration, and if we need to make mass the subject of the formula, mass equals force divided by gravitational acceleration, and therefore 76 newtons divided by 9,8 will give us a mass of 7,8 kilograms. That is solving for mass 3, 7,8 kilograms. The different types of machines that you get, there are 6 types of simple machines. You get the levers, which we've looked at. You get the wheel and axle. You get the pulley, the inclined plane, the wedge, and the screw. Let's look in more detail about the different classes of levers and the components of levers. First of all, the definition. What is a lever? A lever is a rigid item that turns on a pivot or a fulcrum when a force is applied to it. Examples of levers are a seesaw, pliers, wheelbarrow, or broom. Let's look at the components of a lever. First of all, the place where we apply the force is called the effort. The turning point is the pivot or the fulcrum. And the place where the lever applies a force on something is called the load. Let's label the components of this lever. Here we can see the pivot or the fulcrum. Here we can see the load. And on this side, the effort, the place where we apply the force, the pivot or the central fulcrum. And here where the lever applies the force on something is called the load. Looking at class 1 levers. Remember, there are 3 main classes of levers, class 1, class 2, class 3. We're first going to look at first class levers. In first class levers, the following occurs. The fulcrum is between the effort and the load. Examples of these are a seesaw, a crowbar, and an equal arm balance. Let's have a look at this. In this case, remember, the fulcrum is between the effort and the load. There's the fulcrum in the middle. The effort is applied on this side, and the load is on this side. If we look at our example of a seesaw, there you could see the fulcrum, and on one side the load, and on the other side the effort. Looking at class 2 levers. In second class levers, we see that the load is between the effort and the fulcrum. The load is in the central position. Examples of these are a bottle opener and a wheelbarrow. Here you can see the fulcrum is at the end, the load is in the middle, the effort upwards on this side and the fulcrum on this side. Fulcrum and effort on either side of the load. That's a class 2 lever. If we look at the wheelbarrow example, you can see the load is in the middle and the fulcrum on the end and the effort on this end. These are class 2 levers. Looking at class 3 levers, in the third class lever system, we find the effort is between the load and the fulcrum. So the load and the fulcrum are on either end of the lever system and the effort is in the middle. The example is the human arm. Let's have a look at this, where your elbow is your fulcrum. So in the lever system, the fulcrum is at the end, and in the human arm, the fulcrum is the elbow. The effort upwards is in the center between the fulcrum and the load. And in this case, the load is downward of the weight of your arm, or when you're carrying something in your hand, and the load in the lever system here is downwards. And therefore you can see the effort is between the load and the fulcrum. The effort is between, with your muscle pulling your arm upward. There. The effort is between the fulcrum and the load. Mechanical advantage. A machine makes work easier, and its ability to do this work is measured by its efficiency, and we calculate it with a concept called the mechanical advantage. Since the work done by the effort equals the energy gained by the load, we can see, remembering work equals force times distance, that on the one side of the lever, the effort work, remember work equals energy, therefore work equals force times distance of the effort equals the force times distance of the load. And therefore we can calculate on this side of the equation using distance moved by the effort times the effort force equals the distance moved by the load times the load force. We can use a concept or a relationship between the distance moved by the effort over the distance moved by the load, or the load force over the effort force, and this relationship we call the mechanical advantage. Let's look at challenge number 3 involving the calculation of mechanical advantage. Here's the example. Peter is using an effort force of 300 newtons to lift a load of 110 kilograms. Calculate the mechanical advantage of the lever. Let's summarize the data. We can see here's the lever system with the fulcrum in the middle, 110 kilograms, and he is applying an effort force of 300 newtons. You need to calculate the mechanical advantage of this lever. We suggest you pause the DVD and do the calculation. Let's look at the solution to challenge number 3. We asked to calculate the mechanical advantage, and this equation is the load force divided by the effort force. First of all, we need to calculate the load force. Remember, the load force will be the weight of the object, which equals 110 kilogram, which is its mass, times acceleration. And we need to therefore multiply by 9,8 meters per second squared times 110 kilogram, which gives us 1078 newtons. This force is therefore in newtons. And now we need to divide by the effort force. The effort force applied is 300 newtons. So therefore the mechanical advantage equals 1078 newtons, which is the load force, substituted into the equation, divided by the effort force, which is 300 newtons, and therefore we get a mechanical advantage of 3,6. Notice there is no unit since the newtons cancelled out. This is a measure of the efficiency of the system. Mechanical advantage 3,6. Please check your solution. A summary of the equations used in this section. First of all, torque or moment equals the perpendicular force applied times the distance from the pivot or fulcrum. The principle of moments, that the sum of the clockwise moments equals the sum of the anti-clockwise moments. A definition of mechanical advantage, which equals the distance moved by the effort divided by the distance moved by the load, or you could also use the load force divided by the effort force. A summary of the definitions. The moment or torque. The torque or moment of a force is the effect of a turning force. The principle of moments. For any object that is in equilibrium, the sum of the clockwise moments about the fulcrum provided by the forces acting on the object equals the sum of the anti-clockwise moments about that point. Definition of a lever. A lever is a rigid item that turns on a pivot or a fulcrum when a force is applied to it. Right, we have come to the end of the section on moment of force and different types of levers. We suggest you review this DVD a couple of times until you understand the section and practice as many examples as you can. Additional challenges in this section can be found in the Grade 11 Learner's Book, Study and Master, Activity 10, Verifying the Principle of Moments, page 55 to 56, as well as Applying the Moments of a Force on page 56 to 57. Practice your physics and review this DVD a couple of times. Have fun with physics.